Hello and welcome back to Unbounded Operators, the video series where we talk about different advanced topics in functional analysis. In particular, we have already talked a lot about so-called adjoints, and in today's part 10 we will look at an example, namely the adjoint of the multiplication operator. In fact, we will define it on the L2 Hilbert space because this one has a lot of applications. However, as always, before we start with the whole discussion, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. Please don't forget, only because of your support I am able to upload all these mathematical videos to YouTube. So if you like that the videos are freely available, please consider a supporter package on Steady. And as you might know, as a bonus you get a lot of additional material for the videos as well. Okay, then without further ado, let's immediately start with the linear operator t between two Banach spaces x and y. And you already know, in the general setting we have to give a domain of definition, and if this subspace here is dense in the Banach space x, we say that the operator is densely defined. And now please recall from the last two videos that under these conditions the adjoint operator exists. This means it's well defined as a linear operator again, now from the dual space y prime to the dual space x prime. And this t prime is the common notation we have in the case that x and y are given as Banach spaces. And now you already know that having Hilbert spaces here is a special case of that, but then we can also write down a different adjoint as well. This one is written with a star and it does not need the dual spaces at all. Moreover, as we have seen, for Hilbert spaces, these two notions are almost the same. They are just connected by an antilinear map given by the Ries representation theorem. Therefore, if we have Hilbert spaces, we usually would just consider our adjoint t star. And this is exactly what we will do in this video here with the so-called multiplication operator. More precisely, we will take the multiplication operator on L2 with a continuous function. Therefore, first we set x as the space of square integrable functions on R. This means the functions are defined on the real number line, but they are allowed to be complex valued. And now obviously square integrable just means that we take the absolute value of f inside the integral squared. And this integral should make sense and it should be finite. And to be precise, this integral is a Lebesgue integral with respect to the ordinary one-dimensional Lebesgue measure. And also the elements of L2 are actually just equivalence classes of these functions. But with these technical details in mind, what we get here is a nice Hilbert space. Indeed, the corresponding inner product f with g is also given as an integral. And there, as you might know, the first entry in the integral has to get a complex conjugation. Otherwise we just have the product of the two functions and then we integrate over it. Okay, so this is our well-defined Hilbert space x, and now we will define an operator from x to x. And we can do that for any continuous function phi. So this one also maps the real number line to the complex numbers. On the other hand, it does not have to be a square integrable function, but it has to be a nice continuous function. In fact, one can also generalize that and consider more than just continuous function, but here in this video we want to keep it simple. Now the point is, for any such phi, we can define the operator m phi. And as already mentioned, this one should be a linear operator from x to itself. And as always we have a domain d of m phi, which we have to specify as well. But maybe first let's fix the name. This one is called the multiplication operator with respect to the given function phi. And it means that any element from L2f is multiplied by the function phi. This means the image m phi f should be an L2 function again, which we can write down pointwisely. At least we can do that almost everywhere. This means at a given point x on the real number line, our value m phi f of x is given as phi of x times f of x. And obviously this equation works for every x in R almost everywhere. This is always the thing when dealing with integrals and the equivalence classes of functions. We could always change the functions on a set with Lebesgue measure 0. Therefore, whenever we do something pointwisely, we always have to say that this only holds almost everywhere. But obviously this is good enough. This defines the whole multiplication operator. And now, as you can see, the only thing missing in this definition is the statement about the domain of our multiplication operator. And as always, for the domain there is a choice to make, but for the multiplication operator there is a maximal domain possible. And exactly this one we want to choose in our definition. And it's quite easy to explain. Just look at all possible L2 functions f, and then we can do the multiplication with the function phi. So in short, we can call the result phi times f. Obviously, this defines a Lebesgue measurable map almost everywhere. Or in other words, it represents a well-defined equivalence class. And now we can just check if this equivalence class or this function lies in L2 again. In other words, just check the integral with the absolute value squared and check if it's finite. Hence, this domain now guarantees that the image of the multiplication operator lies in X again. So we immediately see that this is the maximal choice such that the operator makes sense. And moreover, one can also easily show that this domain lies dense in our space X. For example, here we can use the knowledge that the C infinity functions with compact support lie dense in L2. And obviously these functions definitely lie inside this domain as well. So obviously the whole thing is not a problem. Our multiplication operator is a densely defined operator, which implies, as we already know, that the adjoint exists and is well defined. This means we can immediately write down the definition of m phi star. It's again a linear operator from X to X, but now with a different domain. And indeed from part 8 we already know the definition of this domain because it's chosen maximally as well. In short, it just considers all possible choices for a function g where we can shift in the inner product m phi to it. And then the equation tells us that m phi star of this g is exactly given as this f tilde on the right hand side. So not complicated at all, it's just defined with the inner product in mind. But at this point the natural question would be, can we say more about m phi star? Can we say that this one is also a multiplication operator again? And indeed, this is exactly what we can show when we look at the inner product again. So we know that the inner product g with m phi f is just an integral. And there please don't forget that g has the complex conjugation on it. And the second part is just the product phi of x with f of x. And now you should see that inside the integral we can just reorder the terms. For example, we can just put phi of x and g of x together, and then we can just put the complex conjugation onto phi and above everything as well. So obviously this is exactly the same integral, but the interpretation for the inner product changed. Namely, now we have a multiplication operator on the left hand side in the inner product. It's m phi with the complex conjugation applied to g. And on the right hand side nothing really changed, there we have f again. So the left hand side is equal to the right hand side, and this holds for all possible functions f and g. More precisely, they have to come from the correct domain, which means the domain of our multiplication operator. And there please note that the domain of the multiplication operator of phi complex conjugation is the same as the other one. So we don't have to distinguish these two domains, which makes everything much simpler. Moreover, now the equality here seems to tell us that our adjoint is indeed a multiplication operator. However, this is not quite correct because we still don't know if the two domains coincide. In fact, the only thing we have shown now is that this nice multiplication operator is a restriction of our adjoint operator. So we definitely know that this domain here is included in that domain. Hence, in the next step, we want to show that the set here given as the domain of m phi star is not bigger than our original domain. So we take an arbitrary g, and then we need to show that this g also lies in dm phi overline. Saying that more concretely, we have the product phi overline times g, and this one should be an L2 function again. So this would show the other inclusion, which means we actually have the equality between both operators here. And here please note, g is definitely an L2 function by definition, but phi is just a continuous function, so it does not have to be bounded at all. Therefore it could happen that the product lies outside of L2. And now the trick is simply, instead of phi, we just work with a bounded function first. So if g is L2 and we have a bounded function h, then the product h times g is L2 again. This is quite clear when you look at the integral, because we can just estimate the whole thing by looking at the maximal value of h. Hence, the whole idea for our proof here is to make our continuous function phi somehow bounded. And we do that by taking characteristic functions we can call psi n. So for every natural number n, we have such a function, and they are easily to define by looking at a sketch. In the interval from -n to +n, we are just at the constant value 1, and obviously outside we want to be at 0. And now multiplying this with our continuous function phi over line, we get a bounded function out. So you see, this is the whole idea. Inside a large interval, we still have our function phi over line, but outside of it, we are just at 0. This makes the whole thing bounded, but pointwisely, we also have a convergence. Indeed, when we send n to infinity, we get out our original function phi over line of x. So these are the two things we need, and now we can go back to our integral. Or to say it more precisely, we look at our inner product again, where now f and g are arbitrarily given like that. So we can definitely form m phi star with g and put that in the inner product with f. However, now on the left hand side, I already want to include the function psi n. The reason for that will be clear when we reshuffle the entries in the integral. As always, we have two parts in our integral, and the first one gets the complex conjugation. However, the complex conjugation will not change our real valued function psi n, because it's just 1 or 0 anyway. This means we can simply shift that to the right hand side as well. This is not a big change, but our inner product already looks different. Namely, now we only have m phi star g on the left hand side. And by the definition of the adjoint, we know that we can push that to the right hand side as well. This means we apply our multiplication operator to the function on the right. And please note that we don't have any problems there, because our function psi n does not change the fact that we lie inside the domain of the multiplication operator. This is quite clear because the function psi n just cuts out a piece of the function f. Hence, now we can finally translate the inner product to an integral again. And now we only have multiplications of functions inside it. More or less the same as before, but now also including our function phi of x. And now you already know, this combination in the middle defines a bounded function. And exactly this bounded function here we want to push to the left. Therefore, in the same way as before, we just have to put two complex conjugations together. And then we see this whole thing now is the new input in the left hand side of the inner product. And most importantly, we know that this input is an L2 function. It's just a bounded function times g, so everything is good. Okay, so this is our final result. As you can see, these two inner products are exactly the same. And the crucial thing is that this holds for any function f in our domain. And since the domain is dense in x, we can conclude that this vector on the right is exactly the same vector as on the left hand side. In fact, this is just a property of the inner product. We know it's positive definite, so there's no other choice that these two vectors coincide. And this also implies that on a pointwise level, the two functions coincide almost everywhere. And exactly on this pointwise level, we can use the fact that the psi n functions converge to 1. Hence, almost everywhere we have the equality that m phi star g is equal to phi over line g. However, since the left hand side here is an L2, we can conclude that the right hand side is also an L2 function. And as you might remember, this was the only thing we needed to show to see that the two domains coincide. So we get our final result. The adjoint is a multiplication operator as well. M phi star is equal to m phi overline. And please don't forget, this overline is just a complex conjugation, so if we have a real valued function phi, it's not there at all. Hence, in that situation, the star operation for the adjoint does not change anything. And these are the operators we call self-adjoint. They are really important for applications, but this is something for another video. So let's meet there again and have a nice day. Bye bye.